Hello, this is Carl Freund with Cambrian-AI Research, and today glad to welcome Blake Johnson back to our program here from IBM Quantum. Hi, Blake.
Hi, how are you doing, Carl? Nice to speak with you again.
Nice to speak with you again. I've enjoyed talking with you in the last week or two about what you guys have been working on, a couple of advances that could materially change the trajectory of quantum. Uh, for the audience, Blake is the distinguished research scientist at IBM Quantum, and he's responsible for the quantum engine. He's the lead there. And we've been talking about a couple things. We've been talking about errors, and we've been talking about dynamic circuits for quantum circuits. So Blake, why don't you start at a high level, help us understand where we are on the road to quantum advantage.
Sure. So this whole enterprise, the kind of why we're doing this in terms of building quantum computers is because of the belief that really the knowledge that a quantum machine, a calculational machine that works with the principles of quantum mechanics, can in principle solve certain problems faster than any other way we know how to calculate, any other way we know how to compute. The problem, though, is in terms of like realizing that vision, actually turning that sort of dream into technology that people can use, is that when we build quantum mechanical machines, they're subject to errors, right? And in order to actually there's kind of a two-step process for getting value. You need to take your problem and convert it into a form that can be executed on quantum hardware, sort of map your problem into a quantum circuit. And then we need to actually be able to execute that quantum circuit faithfully, right, without errors, or with a sufficiently low error rate that the answer to the problem is sort of recoverable from the output of the quantum system. And in my role within the quantum engine, we're specifically focused on that latter half of it, delivering results, outputs of quantum circuits with as low of errors as possible. And that turns out to be an interesting challenge that we've previously thought of purely as from a hardware development standpoint. And this is a major aspect of it as we sort of build hardware with lower and lower intrinsic errors by making better qubits, by making better gates, by reducing crosstalk and sort of undesired sort of physical mechanisms that make the errors likely to occur. But then we're also starting to think in a new way about software methods and sort of protocols that we can layer on top of that hardware that can cope with those errors in a different way. The scale of the problem is really different in the quantum domain, right? Errors occur in your laptop and your phone, but the error rates are so small that they forget about it, right? Like the error rates are maybe 10 to the minus 18, like really small, really rare occurrences. In the quantum realm, we're not afforded such luxuries. The errors are much more common, right? They in sort of the best quantum systems today, sort of the failure rate of a quantum operation is part in 1,000. And so, these errors are sort of intrinsic part of what we're dealing with in trying to convert this into technology. And so we have to be much more mindful about those errors in terms of the systems we build.
Yeah, interesting. So we had talked about approaches dealing with this, right? And you talked about error suppression and mitigation and correction. Can you kind of walk the audience through what those three things are about?
Sure. So right, we have different ways to approach the problem of errors. One approach is known as error suppression, and it's effectively about trying to make the errors less likely to occur in the first place. We can do it through how we design our quantum operations. We can make them sort of more robust to fluctuations in powers and in coherence, make them more robust to crosstalk. There's kind of like pulse control, optimal control methods that make errors less likely to occur. There's even concepts about how you schedule the operations in time that takes advantage of kind of knowledge of the noise or the errors in the systems to again make errors less likely to occur. And there's actually a rich literature from the field of nuclear magnetic resonance, or many of you may be more familiar with the term magnetic resonance imaging from the medical context, where similar kinds of ideas have been developed that can, directly produce, like in the MRI context, a sharper image or higher resolution image, because you've suppressed certain kind of unwanted effects. So one technique is error suppression. Another method is something known as error mitigation. And error mitigation particularly applies to the context where you want to know not what happened to the output of a specific circuit, an individual circuit, but you want to know about sort of the average properties of executions of that circuit. And this happens to be relevant for many applications because we can often represent a quantum solution as some sort of quantum circuit that creates a novel quantum resource state, and then some property of that state. We call it like an operator, a quantum operator, that encodes some aspect, or either the solution to your problem or some part of the solution to your problem. So for instance, these operators can encode the energy of a molecular configuration. They can encode the cost of an optimization function, a cost function optimization. They can represent the output of a machine learning kernel. So I can cast many problems in this context where my solution or my answer is embedded in kind of the average response of some property of the output of the circuit. But that allows me to actually look at more than one circuit execution. And I can actually create a collection of circuits that and use post-processing methods that can allow me to recover a more accurate estimate of one of these operators, one of these observables. The third method the third tool we have in our toolbox is something known as quantum error correction. And this is kind of what's needed for fully fault-tolerant quantum computing. And this also adds additional resource. So the error suppression method was kind of more of a compilation resource that's required. I'm going to sort of change the circuit construction a little bit. In the error mitigation method, I'm going to introduce classical post-processing. So I'm introducing a classical computational resource into how I'm going to get this answer. But I'm also going to introduce additional quantum overhead in the sense of, instead of running one circuit, I'm going to run many circuits, and I have to produce those circuits and process them and so on. Quantum error correction also introduces quantum and classical overhead of different kinds. So we have a quantum overhead of using redundancy in the qubits. So we're going to record one quantum bit, one qubit of information in several physical qubits. And then we're going to add a classical resource in the form of a decoder, which is going to be which I'm going to extract information about the presence of errors in my quantum lattice and use the decoder to find out where the actual errors have occurred, track them, and potentially then get information about how to correct them. So there's different methods that apply sort of additional quantum resource and additional classical resource to allow you to get a lower error in your final answer. And I guess our approach at IBM is to treat error mitigation and error correction on a more similar footing, right? Both of them incur a resource cost, and we want to build technology that minimizes the total additional resource to deliver like the accuracy, the error rate that's needed for a particular application.
So in our discussions, we talked a little bit about that overhead and the exponential overhead of actually doing quantum error correction. Can you describe that for the audience? I mean, we're all familiar with CRCs on normal DRAM to detect and correct single bit errors, but the overhead there is practically zero. What is the overhead of doing quantum error correction?
Well, so it depends. And I guess, it's one of those topics that continues to be continues to gather a lot of activity in terms of people developing novel error correction codes. Some of the most popular codes that we know of today, like the surface code is one example, uses at least like 17 qubits to encode one physical qubit at the smallest version of the surface code, and that can tolerate one error. And if you want to be able to tolerate 2 errors, you need 49 qubits, and so on and so forth. So the physical overhead is large for some of the more popular codes that are out there. There are new codes that can potentially decrease that overhead, and actually, in particular, have a rate, an encoding rate, which doesn't scale as poorly, and that's a promising direction for quantum error correction. The particular thing you were asking, though, well, so I guess to finish that story, once you've encoded, it's a heavy price to pay up front, but then the cost you pay for larger problem sizes scales more favorably. It's like a linear scaling with problem size, as opposed to sort of an exponential cost for larger and larger problems. So at the largest scales, this is why people, when talking about like the long-term future of quantum computing, they're really thinking about quantum error correction and fault tolerance, because in order to get to sort of the final dream of being able to tackle huge problems with quantum resource, like that's going to be the approach that lowers the total overhead for delivering that kind of computing capability. Yeah. There's this interesting intermediate regime, though, however, where error mitigation could offer lower total resource overhead, because it doesn't have the same kind of overhead in terms of physical qubits that are required. It instead sort of has an overhead in number of circuits you need to execute. So there's interesting sort of novel proofs that error mitigation is actually quite powerful. It can deliver kind of unbiased or noise-free outputs in this kind of expectation value context, where you have your problem encoded in an operator. But in order to get that noise-free or unbiased response, requires a number of circuits that you execute, which scales exponentially in kind of the noise of the quantum circuit. So it kind of something that immediately trades off speed with error rates in order to deliver some particular target accuracy or effective error rate in the answer.
Yeah, important work, because obviously, if it takes 49 times more circuits, or 49 times the hardware and the cost of executing on that hardware, it's going to be hard to achieve quantum advantage if every time you try to make your machine bigger, you're going to have to make it 49 times bigger, or whatever the number is, right? Depending on the method. It's going to really erode the value very, very quickly. So
it makes the systems, it really expands the, it kind of blows up the scale of the system you have to build in order to deliver computing capability
level,
with value to the user. So, I mean, that's one of the reasons we're excited about error mitigation, because we think, at least in the near term, this provides a more practical approach towards delivering delivering systems that actually can deliver value to a user.
Interesting. So you kind of need to help the users kind of dial in where they want how much they're willing to spend to get what type of error correction or error mitigation levels as they run their circuits. Interesting. Now, we've also been talking about a completely different area lately, which I found fascinating, which is dynamic circuits, which allow you to really change the capabilities of quantum circuits. Can you talk a little bit about that?
Sure. We've been in an era of executing quantum circuits that are constrained in a way, because the kinds of circuits we've been able to execute previously are things that I would call static circuits. They're ones where they only have measurement at the end, and there's no branching or decision making that happens sort of in the interior of the circuit. This is kind of the quantum equivalent of writing code with no if statements, with no branches, no for loops, right? It's all sort of straight line code. And in some standpoint, that seems inevitable in the quantum context because right, the marvelous things that we can do with quantum circuits depend on being able to have sort of superposition entanglement and preserve quantum states throughout the course of a computation. And once you measure a quantum state, you collapse it into a classical one. So you remove the quantumness that is providing your speed up. But there's been an enormous amount of activity of late, understanding that in fact you can introduce measurement into quantum computations, into quantum circuits, and to do so in a way that can provide different kinds of advantages. So we were just talking about quantum error correction, where you critically need measurements in the interior of the circuit in order to extract so-called syndromes, error syndromes, to detect the presence of errors. But there's other sort of more near-term application domains where being able to introduce a dynamic circuit capability with measurement in the interior has advantages. So in particular, we now understand that you can build algorithms in different ways that may be probabilistic in nature, where you use measurement to sort of herald whether or not you've succeeded. And we also have different constructions that allow you to sort of trade off space, width, and depth in your quantum circuit and use things like teleportation to move data around in a quantum processor. You can't copy quantum data. It's one of the curious things about quantum computing. So you have to move it rather than copy it. And teleportation happens to be one of these Star Trek sci-fi things that you can realize in reality on quantum hardware to move data over longer distances much faster than you can through sort of swapping operations that kind of move qubits between adjacent elements in a lattice. So we have these powerful techniques that are enabled once you can build circuits with control flow, with branching, with measurement in the interior. And we're on the cusp of launching this capability, making it kind of routine on IBM quantum systems. So within a few short weeks, users will be able to execute dynamic circuits that they construct in Qiskit or they construct in OpenQASM, which is a circuit description language that we've developed with the community and executed on IBM quantum hardware.
Interesting. Sounds like this will really open up quantum hardware to solving problems that are currently too difficult to program, to build circuits for.
I mean, I hope what it means is that people get a lot more out of the hardware that is available today. You know, I think what we're talking about in some ways may seem esoteric and in the weeds, and to some extent it is. Right? These are sort of new instructions that are available in the kind of quantum instruction set for building circuits. But the same thing happens in the classical domain, and they end up being powerful enablers for opening up performance of classical processors, right? Like AMD and Intel have for 30 years now been tweaking the x86 instruction set, adding like the MMX and then the SSE instructions and so on, or special purpose instructions for hashing and cryptography. And all these things enable different kinds of workloads, and often numerically heavy workloads, to execute much more efficiently because they can fill the pipelines. They can sort of keep data moving without stalls in those fabrics to get the most out of what those kind of processors can do. And the beautiful thing about all that work is that it's only taken a few specialists working in kind of the, building the fundamental numerical application libraries, things like BLAS or LAPACK libraries, to enable like an entire community of scientific developers or finance applications that are kind of built on top of those numerical libraries as their primitives. So what I really hope happens is that, this will unlock kind of a flurry of activity for those practitioners that are comfortable kind of in the foundations, but the result of their work should ideally, appear then in compiler passes, could appear in in circuit libraries that others can just sort of use and take advantage of the best ways we know how to construct kind of the fundamental primitives of building algorithms with quantum circuits.
Interesting. So build that foundation, and everybody can innovate on top of that on those new dynamic circuits. Fascinating. Well, thank you very much for your time this morning. I look forward to talking with you again. Obviously, quantum's not done, and there's a lot of more work left to do. And I look forward to learning more as we go and sharing that with our audience. Thank you very much for your time, Blake.
Great, thank you. Pleasure to be here.
Talk to you soon.